Hello everyone, very good evening one and all. Welcome to the most comprehensive preparation platform for all competitive exams, BYJU'S Exam Prep, and warm welcome to the GATE 2024 Rankers Monsoon Series. So dear friends, firstly let me apologize for the delay due to some technical settings. There is a delay in the session. So guys, join the session quickly and mark your presence. I am Satya, welcoming you all for this monsoon series today's class. Today's topic is the most demanded topic by students, which is a very interesting topic, very important topic of programming and data structures, that is AVL trees. Yes, whoever have joined the session, kindly confirm, am I visible and audible to you clearly or not? Am I visible and audible clearly or not? Everybody please confirm. Alright. So, without any delay, let me start the session with a quick introduction of mine. I am Satya. I am a research scholar with 15 plus years of teaching experience. I have mentored more than 40,000 plus students, and I have taught I teach programming, data structures, operating systems, computer networks, computer organization and architecture, algorithms, and you can find my other credentials. Okay. So, dear friends, BYJU'S Exam Prep is conducting the national scholarship test through which you can avail up to 90% off on all our programs, and the upcoming scholarship test is on 23rd July and this test would be active live from 9 a.m. to 9 p.m. on this 23rd July. So, register immediately and attempt this scholarship test on 23rd July. Okay. Hi Shyam, good evening. Chalo. So guys, before we understand AVL trees, let us quickly understand what is binary search tree. What is binary search tree? It is a binary tree. Means at most 2 children will be there for any node. So a BST, binary search tree, is a binary tree in which the left subtree will be less than or equal to the parent and the right subtree would be greater than or equal to the parent. Means left one should be less or equal, right one should be greater, big or equal to the parent at every level. That's why I am not taking the term root. Parent. For example, I take one binary search tree. Please observe this: 60, 47, 25, 38, 52, 83, 71, 80. Please observe this binary tree, dear friends. Here at every level you check. Whatever are less than 60, all are left to 60, all are less than 60. Similarly, all the elements right to 60 are greater than 60. So at the root level it is satisfied. Similarly, left to 47 are less than 47, right to 47 are greater than 47. And similarly at 83 also, left to 83 are less than 83, right? Similarly, 25 right is greater than 25, 71 right is greater than 80. So at every level, this left is smaller than parent, smaller than right. So this should be satisfied. Yes, it is satisfied. So this is called binary search tree. Hi Swati. Okay. Now, Before we understand AVL tree along with BST, first we have to know this term balance, height balance. What is the meaning of height balance? Whenever the balance factor of every node in the BST is in the range -1, 0, +1. -1, 0, +1. When the balance factor of every node is either -1 or 0 or +1, then such BST is said to be height balanced BST. Okay. Then now we will get this question. Sir, what is balance factor? Right? Let us see. Balance factor of any node is height of left subtree minus height of right subtree. Left subtree height minus right subtree height. And here please remember, in this balance factor calculation, we will count the height numbered from 1. Generally we count the height from 0, of course, but in this topic we will count the height numbering from 1. And one more important point, please understand, the balance factor of leaf nodes or external nodes will be 0. Leaf nodes balance factor would be 0. Okay. Now let's see one example BST and let us see what are the balance factors of them. Okay. Look at this BST. First of all, is it BST or not? Check. 56 less, all the elements are less than 56. All the elements left to 56 are less than 56, and all the elements right to 56 are greater than 56. Okay. And 25 left one is the smaller than 25. 25 right. Do we have smaller element to write 25? No. You check. 18 is there, 12 is there. 18, 25, 18, 12 are greater than 25. So it is not a BST. It is not a BST. Okay, it need not to be BST for finding the balance factor. For AVL tree, it should be BST. Balance factor you can calculate for any binary tree, right? So let us see how we calculate the balance factor. As I said, balance factor of every leaf node is 0. Here 6, 12, 42, 64 and 88 are the leaf nodes. So their balance factor, you see, it is marked as 0. Right? And balance factor of 18, left subtree 12 is at height 1. I told you height numbering starts from 1. And there is no right child for 18. So 1 minus 0, left subtree height minus right subtree height. So 1 minus 0, which is 1. Similarly, 34 balance factor you look at. Left subtree, this one. What is this subtree height? 12 is at height 1, 18 is at height 2. So 2 is the left subtree height, and to the right there is one element 42 that is at height 1. Right? So 2 minus 1, 1. Similarly, 25 balance factor you check. Left subtree 6 height is 1 and right subtree height is 3. So 1 minus 3 minus 2. In this way, 76 balance factor became 1 minus 1, 0. 56 balance factor 4 minus 2, 2. Everyone understood how to calculate the balance factor? Yes, Please confirm. Did you understand how to calculate the balance factor? Please confirm. Vipin, yes, great. Now, we understood how to calculate balance factor. We also understood how what is BST. Now you combine these two. You combine these two such that in BST, if every node balance factor is either -1 or 0 or +1, that is said to be height balanced BST, that is AVL tree. Here you observe in this example, first of all, it is not BST, so there is no question of checking it is AVL or not. However, you see the balance factor of 56 is 2, 25 is -2, means in -1, 0, +1, are these in this range balance factors? No. So definitely, of course, straight away you can eliminate this because it is not BST. When it is not BST, there is no question of checking for the balance factors. Okay. So what is AVL tree? What is this AVL? These are the initials of the one who invented this. Who invented? This is invented by Edelson, Welsky and Landy. AVL. So these three persons together implemented, figured out this height balanced tree. That's why we call it as AVL tree. So what is AVL tree? It is a binary search tree in which the difference of heights of left and right subtrees, that means balance factor of any node, is less than or equal to 1. This is the absolute difference. Absolute difference. Here less than or equal to 1 in the sense the absolute difference should be either 0 or 1. This means less than or equal to in the sense either 0 or 1. Because if you take the absolute difference, there is no question of minus. In this way also you can understand. Or, sir, we are not understanding this absolute difference. Then you can say -1, 0, +1. The balance factor should be in this range. Okay? If so, we call it as AVL tree. Let us see an example. Let me draw an example. 70, 35, 81, 75, 77, 23, 41, 39 and 9191. Look at this tree. First of all, is it BST or not? Is it BST or not? Let us check. Gamer, yes, you can ask, but at the end. So please stay back till the end. At the end of the session, you are welcome to ask any other question. Okay? Is it BST or not? Check it out. 70 less than elements are left elements are less than 70. Right elements are greater than 70. Yes, at root level the condition satisfied. Now 35 left element 23 less than 23. 35 right greater than 35. 41 left less than 41. 81 left less than 81. 81 right greater than. So it is BST. So the first rule is satisfied. It is BST or not? Yes, it is BST. Now calculate the balance factors. All the leaf nodes balance factor would be 0. What would be the 41 balance factor? Left 39 is at height 1. There is no right child for 41. So 41 balance factor, wait a minute, let me change the color. 41 balance factor would be 1 minus 0, 1. 75 has no left child. So left subtree height is 0 minus right one, 77 is at height 1. So 0 minus 1 minus 1. So 75 balance factor is minus 1. 91 leaf node, its balance factor is 0. Now 35 balance factor, 23 is at height 1, 41 is at height 2, means the right subtree is at height 2. So 1 minus 2 minus 1. 81 left is at height 2, 91 is at height 1, so 2 minus 1, 1. And 70 left subtree height is 3, right subtree height is also 3, so 3 minus 3 is 0. You check the balance factors, all the balance factors, all are either 0 or minus 1 or plus 1. So all the nodes have the balance factors in this range. So the second condition is this balance factor is in the range minus 1, 0, plus 1 for all the nodes? Yes. So as these two conditions are satisfied, it is called height balanced BST, which is called AVL tree. Hope this is clear for everyone. Hope this is clear for everyone, right? Now comes the question. Why to check this? What is the advantage of doing this? The advantage of this balancing is to make the time complexity from linear time complexity to logarithmic time complexity. For search operation, for insertion operation, for deletion operation, for search operation or insertion operation or deletion operation in the BST, in the worst case, it takes big O of n time, but when you balance and make it AVL tree, then the time complexity becomes log n. So to make this linear time complexity to logarithmic time complexity, this balancing is done. Now comes the question. How to balance? Okay, we have got some tree which is not balanced. Means some node balance factor is not in this minus 1, 0, plus 1. Let's say it is some 2, minus 2, 3, other than these 3, other than minus 1, 0, plus 1. So how to balance such tree? The solution is by making rotations. So to balance, we do either of 4 rotations. What are they? LL rotation, RR rotation, LR rotation, RL rotation. Left rotation, right rotation, left rotation, right left rotation. When you do left rotation, before that let me tell you the node which is not balanced, the node which is having balance factor, the node which is having balance factor other than minus 1 plus 0 plus 1, that node is called critical node. So imbalanced node is called critical node. So in the further discussion, when I use the term critical node, please understand that is imbalanced node. Okay. Now, when we do left rotation, when a node becomes critical because of insertion of some new node to its left, to my left and its left, a new node is inserted. Because of that, I became critical, I became imbalanced. Then we do left, L rotation. Similarly, to the node is inserted towards right, then critical, then we do RR rotation. Left's right, LR rotation. Right's left, RL rotation. Right? So let's see what is LL rotation. LL rotation. Check it. First we have AVL tree. The leftmost diagram is AVL tree. 100, 50, 25, 75, 150. It is balanced as well as BST. So it is AVL tree. Now we have inserted 12. A new node is inserted to the left of 25. Now if you calculate the balance factors, 12 balance factor 0, 25 is 1, 50 is 1, 75 0, 150 1, 100 2. So which is critical? 100 is the critical node. Why it became critical? Just earlier it was non-critical. Just before insertion it was not critical. Now it became critical suddenly. Why? Because a new node is inserted to its left. Left's left side. Left doesn't mean to that left node. What side? Yes, the new node is inserted towards its left. Okay. Now what we do? We apply LL rotation. Dear friends, it's a mirrored representation. Means though it is left, how we represent it as right arrow. As right arrow. So always remember the critical node, let it be A. Left we are telling, so this is B, this is C. Always remember this terminology, A, B, C. Now A is the always critical node. Okay, critical node you have to always mark as A. Okay, it's left we are telling, so its left node is B, that left node is C. Now whenever you make LL rotation, see, when you have three nodes A, B, C, while A is critical, whenever you do left rotation, B becomes root, C will be as it is at the left side of B, and A becomes right child of B. Now comes the question, sir, A might have some right subtree, B might have some right subtree, C might have left subtree, right subtree, though C we are not changing, so C will be as it is. Now where you will place A right subtree? A right subtree would be on A right side only, so there is no change. If suppose C is having some left and right, that also has no impact. But where you insert this B right subtree? B right means it should be on the right side of B. So after rotation also it would be on the right side of B only, but as left child to A. So B right subtree would be on the left side of A. So that is what happened here, you see. Now whenever you do LL rotation at A, B becomes root. This is B. Right? So this is B right subtree, guys. This is C left. This is A's right. So A right is as it is as A right. A becomes right child of B. B becomes the root node. Right? Swati, Shyam, Gamer, Vipin, hope you are all following it. And C and C left has no change. C left, earlier they were left to B connected to B, now also they are left to B connected to B. A right also has no impact. Now B right, where to connect B right? After rotation also B right will be on the B right side only as A's left. A's left. So this is what LL rotation. LL rotation. Okay. Similarly, let us look at RR rotation. Suppose we are having a balanced BST. To this, we are now inserting one node 100. Because of that, two nodes became critical. Two nodes became critical. 67 became critical. 85 became critical. So when there are multiple nodes more than critical, always you have to balance from the critical node, or I can say balance the bottommost critical node. The bottommost critical node. When multiple critical nodes are there, when multiple nodes are critical, always balance the bottommost node. When you balance the bottommost, automatically the top gets balanced. You will see that now. Here 85, 67, two imbalanced nodes we have, two critical nodes. So what is the bottommost node? 85 is the bottommost node. So balance that. How to balance? I said always mark critical node as A. Towards right now. Why A became critical? Because towards A, right side, its right side you have inserted a new node. Because of that A became critical. So you have to do RR rotation. As I said, you will represent it as mirrored image. That means though it is RR rotation, we will represent with left arrow. Left arrow. So when A, B, C you take, when you have A, to A there is B, to B there is right side C. A has some left part, B has some left part, C has its left subtree and right subtree. Whenever you balance it, what happens? Whenever you do RR rotation at A, what happens? B becomes root, C has no impact, means C left and C right will be same. A becomes B's left and A left has no impact. Now, where to insert B left? After rotation, also B would be on the left side of B left would be on the left side of B only, but as A's right. As A's right. That is what happened here. So whenever you apply RR rotation at A, 85, 90, 100 are B and C, B becomes root. So B becomes root and A would be on the left. C would be same as right, and there is no left and right parts. So that's it. If at all we have, we will add as per this rule. So this is what RR rotation. Okay. Similarly, quickly let us see LR rotation. What is LR rotation? Left, right. So if there exists a AVL tree and you are inserting a new node, because of that one node became critical. So now from that critical node perspective, you check Why it is critical? Till now it was not, but now it became critical. Why? Because you have inserted a new node where to this 78 left side to that right side. Left, right. From the critical node perspective, you have to see. Critical node means which one you wanted to balance. As I said, when there are multiple critical nodes, you have to take the bottommost. So from that, from the bottom node or bottommost critical node perspective, where insertion took place, that we have to check. So left, right. So now you have to do LR rotation. Now again, critical node, take it as A, left one B, right one C. A, B, C. Always these three literals you remember. Now, whenever you do LR rotation, A left there is B node, B right is C, A has some right subtree, C has some left and right subtrees, B has some left subtree. Whenever you do LR rotation at A, see, C becomes parent, C becomes root, not B, C becomes root. Okay, C becomes root. And A right will be C right child, B left has no impact, means B left will be like C and A we have swapped actually. In the A place C has gone. So B is still on the same side. On the same side. B left has no impact. Now C left, C right we have to insert. Where C left would be on C left only, but as B right. C right would be on C right side only, but as A's left. So this is what the general equation or method. Now you apply that on this example. So whenever you do LR rotation here, C go to the C 75 go to the root place, and AR come to the right part of C. B left are in the same position. Now C has only left child in this example. So C left would be still on C left side only, but as B's right side. Simple. So this is what LR rotation. We call it as a double rotation, dear friends. Actually it is right rotation then left rotation. Okay. Similarly now RL rotation. So after these three rotations, now you can understand what is RL rotation. If there is A right child is B, B left child is C, B has its own right subtree, C has its left and right subtrees, A has its left subtree. A is the critical node. Whenever you apply RL rotation, C becomes root, A and AL will be on the left to C, B would be on the same position, B right also would be on the same position, C left now becomes A's right, C right now becomes B's left. So here 90 is the critical node. Due to insertion towards 90's right left side. So here this is C, this is B, this is A, and this is B right, this is A left, this is the C left. So just observe that. C becomes parent, C becomes parent, so 95 becomes root. B and B right would be on the same position. A left will be on the left side of C, and C left becomes A's right. Got it? So, do you understand what is RL rotation? So balance factor should be either -1 or 0 or +1, and it should be BST. Then we call it as height balanced BST, which is AVL tree. The advantage of AVL tree is it will perform in search operation, insertion operation, deletion operation in the log n time complexity in all the cases. Of course, the space complexity for n nodes, it is n. So leaving that, time complexity, when I talk for all the operations, AVL tree take logarithmic time complexity irrespective of the insertion order. But BST takes n. That's why we have got AVL trees. Hope it is clear. So that is what about AVL trees, guys. Hope this session made you clear about this AVL trees, and it is really interesting topic and important topic too. So with one more interesting topic, let us meet. Okay, I wish you all a happy learning, and dear friends, please do like, share and subscribe to our BYJU'S Exam Prep YouTube channel, and please enable the notifications. Yes, that's all for today. Thank you so much. Yes, gamer, now you are welcome to ask. Yes, gamer. Hash table has 100 records. Probability of collision before the table is 10% full. 10% full in the sense 10 records should be full. Those 10 records should be having the collision, right? Before 10% full, collision should occur. Means before 10 records should fill, collision should occur. That could occur in the first insertion, or second, or third, or fourth, or fifth, or sixth, or seventh, or eighth, or ninth, or 10th. So it is something like 1 by 100 plus 2 by 100 plus 3 by 100, so on. Maybe 55 by 100 you will get 1 plus 2 plus 3 plus so on till 10. So it could be some 55% kind of. And again it depends on that collision resolution technique. But just as a general, if we speak, this is how you calculate, because the first insertion should be collision. Out of 100, any one you can, any one slot you pick up. That is what, as a general, the approach I said, gamer. So if there is a proper question, then definitely we can solve it. But the meaning of the question is this, and this is the approach what I said. Okay, you please send me the total complete question and options in my Telegram group, so that I'll send you the solution. Okay, thank you guys. See you on the next class. Till then, have a great time. Take care. Good night, everyone. Bye bye. Yeah, I think it is 1 by 100. Sorry, 100 by 100, 99 by 100. Sorry, in the probabilities I took something wrong. Okay, gamer, please send me in the Telegram group. I will send you the solution.